Hi friends, and welcome to a video I'm doing here on the n+1 query problem and how it relates to GraphQL. So this is actually something that I encountered in my professional life, now twice now actually, in two different separate contexts. But so in this video, we're going to be talking about what exactly the n+1 query problem is, and how it affects performance of your backend services, and how you can fall into this trap pretty easily if you're using sort of standard GraphQL tools and libraries for whatever programming language you're using, and you're not even conscious that this is happening to you. It's pretty easy to sort of naively write your GraphQL servers and not even know this is necessarily affecting you, unless of course you're looking for it and doing some performance profiling. Before we sort of delve into how this relates to GraphQL, I do want to talk a little bit about what the n+1 query problem is, and just generally with how this fits in with just writing generic backend services that are data oriented. Most backend services that you see for business apps are some kind of stateful application that has some data stores, and in these data stores there's entities, and these entities make sense for your particular business. So we're going to make up a system just so we have some concrete entities to talk about, and so that's what these two programs here are. So this is going to be like a ticketing system. So you can imagine something along the lines of maybe Jira or GitHub issues, something like this, where or maybe even like a to-do system where there's tickets. So this is a kind of entity, is a ticket, and then each ticket has maybe some content and identification, and of course an author, right? And then this author might be another kind of entity, in this case maybe a user, and that might have another ID and maybe a name for this user. And so right here we have two functions, and they're the same. They do the same thing. So they're going to find all the authors for all the tickets, right? And one is gonna have some problems, and the other one is not. And so, if you were just kind of writing this naively, you'd say, okay, well, I'm gonna make some authors, and then I'm gonna ask my ticketing service, whatever this is, it doesn't really matter, necessarily where this data comes from. Maybe it's coming from a database, or maybe it's coming from REST calls to another service in your service-oriented architecture, whatever the case may be. And so then once you have all the tickets, you're going to iterate over the tickets one by one, and then you're going to, so the ticket will tell you the author's, user ID, and then you're going to ask the user service for that user, and then, put it into the collection that you're accumulating. And so if you're just even a little bit savvy at backend engineering, you're like, oh my gosh, this is a problem, right? Because what we have done here is we've done one, they call it the n+1 query, but it doesn't necessarily mean we're doing a query. But so we've got this one query here to get all the tickets, and then for n tickets, we're doing another query for that singular user, right? And so the performance of this thing is typically bad. Maybe if tickets is a small collection, maybe whatever, you probably wouldn't even notice. But the problem with it is as it this scales, right, relative to the number of tickets. So for every ticket that gets added to the system as users start using your product, whatever, the performance of this is going to get worse and worse. And that's because as this collection grows, we're going to be doing more and more queries for those authors. And this suffers from a number of problems, not least of which, of course, is that your latency keeps getting longer and longer, right? Because however long this call takes, you're going to do that n times, and they're in serial, right? So the latency of something like this can get quite large quite quickly. So this is, by the way, where that name n+1 query comes from, is because you have this +1 query at the top, and then you do n queries for some collection, right? And so here's your n queries, this little for loop. So if you are using like an ORM or something like this, maybe for your data layer, there are lots of ways to sort of circumvent this. Like for instance, in Ruby, if you're using active record, you might have an includes. You might say something like tickets where or whatever, and then includes author. or whatever. But if you're doing this by hand manually, you might write something like this instead. So rather than collecting authors directly, you might just collect up all the IDs from each ticket. So this is, this is not doing a query. And then at the end, you're actually going to do a single query, sort of batching up all those author IDs. And so you need, in this case, you need a service. Your user service has to also support sort of a batch API, which is that rather than, one ID at a time, I'm just going to give you like all the IDs, and you can kind of fetch it at once. And just another way of illustrating this same point, we can imagine that if we have, these services are talking to each other over HTTP, we might have a GET request for tickets. And then if we're writing it sort of the naive way, we're going to have one GET request for every single ID of all those tickets, all those authors, right? Another more efficient way to write it would be, okay, one GET request for all the tickets. That's the same as this up here. But then you have a batch version, and so to a single GET request, you just send it all the IDs you're interested in. If you want to think of it in terms of SQL, because this is called the N+1 query problem, so I thought I'd write some SQL. This is, again, this sort of same expression, just in a different form, right? Where, we're going to select all the tickets, and then we're going to make, n selections for user, where that particular, which for each author ID. Of course, if you're writing more efficient SQL, more batched SQL, you could write something like, again, for all the tickets, and then you're going to say, well, get me all the users where the ID is in author IDs, right? And so this is the batched up collection of IDs, one of many, right? So now that we sort of have a sense of what the N+1 query problem is, let's think about this in terms of GraphQL. So what I have done here is I have a little repository, and I will of course link this in the description of the video. But this is just like a plain old GraphQL server. There's nothing special about it at all. So I've used Express, and this is just for some request logging, which we'll use later. And then it has a single endpoint, /GraphQL. This is all the standard Express GraphQL APIs. I haven't done anything special here. This is like exactly what you would do if you're just like getting up and running with a GraphQL server in Node. Now, this problem, of course, does not limit itself to JavaScript. You'll encounter this problem with many GraphQL libraries in many different languages, and I've tried to make this as easy to understand for people who don't necessarily use or know JavaScript. JavaScript is pretty readable for most people, and you'll have to. I'll try to mention it as we go. You'll have to look up how to do particular things in your version of a GraphQL library, or what's idiomatic in your programming language may not be necessarily idiomatic in JavaScript. So do keep that in mind as we go, but. The high-level concepts will be applicable in any library, hopefully. So anyway, I have this basic server, and it's got this endpoint /GraphQL, and let's just take a look at the schema. So here's the schema for this GraphQL endpoint. So it's in this file here. And so the schema looks something like this, right? So we have the top level query, which has, a single field called tickets. It gives you a list of tickets. Each ticket has an ID, an author, and some content. And of course, an author is another type, a user, and it looks like this. And so this is basically the GraphQL expression of the system we were just discussing just a moment ago. And so if we take a look at what the schema looks like, okay, so it's got a query, there's that field tickets, it's a non-null list. And so each field, of course, has a resolve function. So depending on what your programming language or library calls this thing in your version of your GraphQL library, it might be called something slightly different, but you have some kind of function that can actually return the data, right? And I have wrapped these functions in some profile, these higher order functions here, they just wrap it with some profiling. We will see as we actually run and execute this program what these profilers do. And they're just going to print starting and ending, maybe some time latencies measurements. And so okay, so it's pretty boring. We ask the ticket service to get me all the tickets. And then, for each ticket, these are just regular old, just reading fields basically. And then of course, for each ticket, if we want to get its author, we ask the user service, to fetch that user by the author ID. And of course, the user type is pretty boring. These are all fields that are fetched for us by the user service, right? And that's really it. And now, if we sort of take a step back and we think, so I'm actually going to pull this up. This is a graphical thing that is running and connected to this local server. So I'm just going to issue a query here for basically all the fields in our schema, and, and get some kind of response. Oh, I got to run the server. That would help. Okay, so that's running, and of course, we get some data back, right? So this is like these are some in-memory data structures that I built so that we're not actually talking to a server, or I'm sorry, we're not actually talking to a data store. This is all just stuff that's stored in memory. But as we will see in these data services, I've induced some latency to make things more obvious. So let's actually take a look at those services real quick. So this is, of course, where the data is coming from. So let's look at user service, for instance. So I'm making the call to get user ID by ID sync. And so what this is doing is it's sleeping for some amount of time, and then it's returning, just some in-memory data, right? So this is like exactly what you would see if you were like talking to a database, for instance, or making a REST call to another service. There's going to be some latency involved there, even in your like high performance, low latency, like sort of local area like cloud networks or whatever. There's of course going to be latency there. This is fine, but like if I'm like an engineer and I want to make my the performance of my services good, and I'm like profiling. So here's an example of this request here. I'm profiling my GraphQL query, and I'm like noticing that like, wow, man, like this is like like if we take a look at what this is doing, we basically got 3 tickets and like 2 authors, and like we're like, whoa, up to 600 milliseconds for this whole thing, and it's like, what is going on? And so if we look at these logs that I have put in, so I have a start and an end for each resolver and each service call. And so it kind of makes this nice little stack. But basically what it's saying is, okay, so first we're starting that resolution for all the tickets, and then we're going to make that service call for all the tickets. The service call is going to return, so this is 150 milliseconds of like sort of induced latency. And this probably wouldn't be what it would be in your service, hopefully, but I've just made this number like large enough so that we can actually see these exaggerated effects, right? And then, of course, for each one of those tickets, we know there's 3 of them. We notice that, oh my gosh, that like we're making a service call for all those users. And if we just take a step back, like this actually makes a ton of sense just from a naive standpoint that like, well, if my job is to implement a GraphQL server, right? Like my sort of input string is this thing. And it's like, just naively, like I'm thinking to myself, oh, okay, like I got to read these fields one by one. So I'm going to like ask the user code, hey, please resolve the tickets field. And that's going to give me back a list of tickets. And then for each ticket, I'm going to, resolve the ID field, the author field, the content field, etc. And then so on and so forth. And just, sort of recursively resolve all these fields, one by one. And so as a person who is writing the schema, so as a sort of a user in the user code space, I'm just writing resolve functions. And I don't necessarily, for instance, in this author field, I don't necessarily know if this ticket, my context, this ticket that I'm sort of resolving recursively under is part of like an end query. I don't have that context here, right? Like there's no way for me to sort of know that, right? And so that's where this N+1 query problem sort of rears its head in the GraphQL context, is because, well, shit, like the way in which GraphQL libraries are architected, each resolver is meant to be highly reusable and sort of context-free of where it is in the graph, right? And so we don't inside this thing, we don't know that we're hurting our performance by doing this, right? So, and that's why ultimately this whole thing right here is like, oh man, we took 150 milliseconds for the all tickets. There's not really much we can do about that. But then we did 3 separate calls to users in serial, and then of course we ended up with 600 milliseconds of latency at the end. And so like, okay, how, like now that we've sort of established, where this problem comes from, how do we solve it? Well, firstly, I do want to point out that the version of this program that I have written is synchronous code, right? All these service calls are end with this sync suffix here. I understand that this is not idiomatic JavaScript, but I did this on purpose. And I also did this because some people watching this video may not be using JavaScript, where synchronous code is sort of the default. Blocking code is the default. So, for instance, if we were writing in Ruby on Rails and we were using active record, this line right here might be like a call to the active record ORM, right? We might say something like, ticket.author, and that .author might be, some ORM call that makes a SQL query under the sheets, right? So the first way to sort of mitigate and make this problem better is to switch to asynchronous code, right? So as we noticed, like way back in this first program we were looking at, let's pull that back up. We noticed that like if we block on this line, we can like sort of like that you imagine a waterfall of call stacks where each one, this latency gets this tail that gets longer and longer, right? But what we did here is we batched them up, and if we're just thinking like, oh, what if there was a way, what if there was some, between these two things where, oh, instead of waiting for me to get this author back, I'm just going to keep going, right? I'm going to keep iterating over tickets because I know that each service call for an author doesn't necessarily depend on the previous one, right? It's not as if we're using, author 1 to compute author 2, right? They're all sort of independent in a very like real dependency sense, right? So if there was some way to for me to do something like maybe like that, now this wouldn't quite work exactly as written, even in JavaScript, but if there was some way for us to sort of overlap, especially since this is probably I/O driven, right? Maybe it's doing network requests or database queries or something like this, or maybe even you're reading files or whatever to, whatever. If there's some way for us to overlap all that stuff, we can cut our latency by a lot, right? And so if we just take a look at those services again that I was showing just maybe 5 minutes ago here. So I wrote a synchronous version, and then I also wrote an async version, and I just dropped the suffix because at least in JavaScript, this is the more idiomatic way to write things is, for things to already be asynchronous, right? So in this case, I'm sleeping, but I'm doing the sleep asynchronously, and so all of these sleeps will overlap, right? And so we can actually demonstrate that very quickly. So instead of making a synchronous call here, I'm going to do that, and I'm going to do the same thing down here, although we'll notice that probably it doesn't matter here for at least our particular case, right? So let's restart this server. I'm going to issue a new request here. And then, okay, so now the output looks different, and we notice that our latency went all the way down, basically halved, right? And that's great. And so we noticed by looking at the output, it's kind of overlapped, where here it was like one after the other. So right away, we noticed that the GraphQL server, if you return a promise, so that's the asynchronous mechanism in JavaScript, it can keep going, right? And so you'll have to look into your particular programming language, or what's idiomatic for your programming language, or maybe just what library you and your team like to use. Like maybe you're using observables, or if you're in the Rust ecosystem, maybe you're using futures, or whatever the case may be. You need some mechanism for sort of to tell the GraphQL resolver that I haven't found the user, my entity yet, but you can keep going, and just eventually I'll give you that user value later, and that's fine, right? So again, you'll have to look at your particular programming language how to do this, but in JavaScript, of course, promises are available, so that's what I've chosen to use here. So again, each user still took 150 milliseconds, but they were over interweaved, and we've already cut our latency in half. And actually, to be honest with you, as far as latency per request is concerned, this is about as good as we can do, right? We have to make at least one call to the user service and one call to the ticket service to get the data we're asking for. So 300-ish milliseconds of latency is about as good as we can expect, right? But even here, right, we're not totally satisfied. So while we have cut our latencies, we're man, there's I wish we could do better, right? Because we've noticed that we're making 3 calls to the user service. It would be nice if we could give the user service like maybe a slightly more efficient or like maybe increase our throughput, right? So the number of requests we can handle by like batching this up, right? And so here's where we can actually get even more efficiency, right? So you'll have to look again in your particular programming language, or maybe like what libraries are out there for your, or maybe like sort of a counterpart library for your GraphQL server library, whatever the case may be. You'll need something that usually is called a DataLoader, right? And so maybe you've heard of this online before, like what is a GraphQL data server or DataLoader? What does it do for you? And so essentially what a DataLoader is it's a place for you to kind of store up information that you will at a later time use to resolve fields. And so more concretely, if we're taking a look at this author resolver, it would be nice, instead of calling the user service right away, what if we called this like maybe like not even a server, we'll call it, or I'm sorry, not even a service. What if we called it a data loader? And we told this data loader thing, hey, I want you to like take this author ID and like kind of store it, hold on to it. And then at a later time, and so again, this will be dependent on your particular programming language, how this is eventually scheduled. But at some point, maybe the GraphQL server code, or maybe if you're just using JavaScript, maybe like some asynchronous like set timeout has completed, or whatever the case may be. That data loader will be like, okay, it's time for me to kind of flush, right? And so it will take all of the IDs that you have sort of batched up, right? And it'll like make one service call that you configure when you create the data loader, and sort of make all these calls at once, right? And so here's how we can not only, we've already increased decreased the latency of our service, but we can also like maybe increase the throughput, right? Get some more performance, more efficiency, especially out of our downstream user service, right? So here's what that might look like. I'm just going to pull up the main code again. So most GraphQL servers have some way to give some values to every single resolver. And so we want to kind of put these data loader things in the global context so that any resolver at any time can grab a hold of them and like say, oh, I want to put something in the queue, right? It's so to speak. So what I'll do here is I'll just get loader. I'll just write a function here. And so I've already written this function. So it's something like, and we'll just take a look at that actually. We'll pull it up right now. Services, loaders, okay. Actually, so it's this build loader getter. Okay, let's do that. Loader getter. Okay, and then we need to import this bad boy, const build loader getter, not that syntax. This is in services / loaders. Okay, and let's just take a quick gander at the implementation of this thing. It's actually not very complex. And again, the nature of what this function looks like might change depending on your particular programming language or whatever. But so what I've done here is it's a function. I call this function and it returns me a getter. It returns me a factory, so to speak, and I have that factory is going to be backed by like a weak mat cache. And so what this is really doing is it's sort of lazily creating one of these data loaders. And so maybe the way in which you do this in your particular production environment or your programming language might vary. Again, like the instructions of how to do this for your particular use case or programming language or whatever will probably be available with the data loader library that you choose. But anyway, so long story short, it's, if we have the loader of a particular service, we're just going to return it. Otherwise, we're going to create one. And when we create the new data loader, so in JavaScript, the library is literally called DataLoader. Great name, right? We're just going to ask the data loader, or we're going to give the data loader a batch function. So again, if we just take a look at our service for users, we have this nice batch API, right? So instead of a single ID, it takes an array of IDs, and then it gives you the user per ID, right? And so this is our batch API, and so our data loader is now configured with that batch function, right? And so now that I have sort of put the loaders in the context, if I go back to my schema right here, and I'm just going to change the resolver of the user. So I'm going to say something like loader equals context.getLoader. And so I have to ask for the particular one I'm interested in, and I'm interested in the user service version. And so then I'm going to say loader.load, and this is going to be ticket.authorID. And again, so what this exact function is going to look like is going to be mostly dependent on your particular programming language or which library you're using for GraphQL or whatever. But essentially, the DataLoader library in JavaScript has a .load, and .load is what you pass to sort of put that ID in the queue, right? And so in JavaScript, .load will return a promise that will be later resolved once that batch function has actually been executed. And the data loader will take all those IDs that were batched up and then again, like sort of multiplex that out, or maybe demultiplex that out. I'm not sure which direction we're talking here, to each resolver that asked for it within a singular context, right? So let's see if we can do that real quick. So now that we have this, we'll see if we can run our server, and then we'll execute the same thing. And so now this is like looking better than ever, right? So again, we still have our 150 millisecond of latency for all tickets, but we've actually started 3 resolves for 3 different authors. That makes sense. But we've only made one service call, right? And that service call only took us 150 milliseconds. And so again, we're down to 300 milliseconds of time, and that's pretty good. So the question, one question that sort of arises out of this, I think, is, when should you use data loaders, and when is it like appropriate? You may also like think that like, we've kind of increased the complexity of our code, although not that much, right? Our resolver really hasn't changed that much. But we've kind of increased the complexity of like, we've had to pass this context through and all this other stuff. So, is this a premature optimization, right? In my experience, no. Just given the nature of how GraphQL works and what kinds of queries that people are going to be asking for as client engineers, you're going to have lots of dependencies between these entities, and this is really the only way to get good performance out of it, not only from a latency perspective, but just the throughput. As you start handling more and more GraphQL requests, if you're not careful, these inefficient loaders or these inefficient resolvers are really going to start to pile on your downstream services and just, murder performance. Okay. So the only other thing I wanted to sort of mention here is like, well, there is one additional thing that is kind of cool here. And again, this depends on your particular data loader library or whatever the case may be. But this also provides a nice place for caching, which is like another benefit. You can, of course, I think, for instance, in the JavaScript data loader library, you can just ask to turn caching off. I think it's on by default. But it's at least for an in-memory cache. It's very likely that GraphQL queries are going to ask for the same entities over and over. You don't need to keep batching the same IDs over and over and asking the downstream service for the same IDs over and over, especially given how GraphQL tends to work. GraphQL tends to work as, you sort of do all your writes at the beginning and then all your reads at the end. And once you've sort of entered the read part of your query, that's really it. There's, you can safely, at least per request, cache things up. So by default, most data libraries will just like cache this. So once an ID has been fetched, if that entity is asked for again in somewhere else down in the GraphQL query, it won't even bother your service. It'll just immediately resolve with the correct value. So I think we've mostly covered it. Again, my recommendation is like basically as soon as you start using GraphQL, find the data loader equivalent in your particular programming language or whatever, and try to use asynchronous code. And with those two things together, hopefully you can increase the performance of your GraphQL API. Well, that's pretty much it. This code will be available on GitHub. I'll be sure to link it in the description. Thanks for watching.